today we start with the diagonal canonical form. In this we will study introduction to canonical form of modeling, then state space representation of canonical form of modeling. Now about the introduction to canonical form of modeling. The first point, the state model having minimum number of non-zero elements are called as canonical forms. So, you will find that in this particular form the number of non-zero elements are minimum, other elements are maximum zeros. Second point, there are two types, one is diagonal canonical form and second one is Jordan canonical form. Diagonal canonical form is there are eigenvalues which are distinct, they are not repeated, that is called diagonal canonical form. And second one, Jordan canonical form means there are some eigenvalues which are repeated. This method is based on the concept of partial fraction expansion, because when we do the model we have to apply a inverse Laplace transform. So, if you take the normal model, it is difficult to determine the inverse Laplace transform. So, in this case we have to use the concept of partial fraction expansion. Last point, this form is useful in checking controllability, observability, state transition matrix and also in model order reduction techniques. Controllability observability is very important in controller design, particularly in state space analysis. Therefore, when we will study controllability and observability, at that time we should also get the idea about the canonical form of modeling. That means this canonical form of modeling is required in case of controllability and observability. Then about the state transition matrix and model order reduction technique. Model order reduction technique means that when a system is of higher order, that can be reduced to lower size. So, that time also we can use this type of modeling, that is canonical form of modeling. Now, here there are two parts. In part 1 we will see diagonal canonical form where degree of denominator is greater than degree of numerator, and we call this type of transfer function as strictly proper transfer function. And in another part we will see, right now we will study the degree of denominator is greater than the degree of numerator, that is strictly proper transfer function. Now we start discussing on this issue. So, in order to get the canonical form of modeling, that is the diagonal canonical form, we start with a transfer function model. For simplicity, we will take a third order system. So, I am writing down the equation of transfer function y of s divided by u of s, that is equal to a2 square plus a1s plus a naught. So, this is your third order system. Now, here this has to be converted into canonical form. So, here we assume that the eigenvalues or roots of this are different eigenvalues. Therefore, what we will do, we will write this transfer function as ys by us equal to C1 upon s plus lambda 1, C2 upon s plus lambda 2 and C3 upon s plus lambda 3. So, here transfer functions. Now, here we have written in terms of s plus lambda 1, lambda 2, lambda 3, and that means we should know the eigenvalues of this denominator, that is lambda 1, lambda 2 and lambda 3. Now, afterward what we will do, we can write this ys by us, that is equal to, so we solve it. So, what we will get? We will get here s plus lambda 1, s plus lambda 2 plus s plus lambda 3. Now, if you solve it, what we will get here? We will get C1 s plus lambda 2 into s plus lambda 3, that is C1, plus we get C2 write down as s plus lambda 1 S plus lambda 3 and C3 we write down as S plus lambda 1 S plus lambda 2. So, here we will find that we have written the equation in terms of Ys by Us, and like this C1, C2, C3 we have written like this. Now, what will happen, this A2 S square A1S and this. So, both the equations are same. So, what we can do, we can compare this equation with this equation. So, if you compare this equation, what we will get, we write down as A2 S square plus A1S plus A naught equals to C1 S plus lambda 2 S plus lambda 3 plus C2 S plus lambda 1 S plus lambda 3 plus C3 S plus lambda 1 S plus lambda 2. So, this equation we have written. Now, our main purpose here is to get the values of C1, C2 and C3. So, how to get this value of C1, C2 and C3? So, we will find out there are two options. One option is that you can directly solve this equation and compare the coefficient of S square, then S1 and S0, but that will be a tedious process. So, in order to tackle this one, what we can do here, that we replace the different values of S. So, initially what we will do, we can replace, if you replace S equals to minus lambda 2. If you replace S equals to lambda 2, so what will happen? So, we will get the equation as here A2 lambda 2 square minus A1 into lambda plus A naught. What we have done? We have replaced S equals to lambda 2 in this equation. So, what we will get, lambda 2 square A2 minus A1 lambda 2 plus A naught, that is equals to, when we replace S equals to lambda 2 in these equations, what will happen? This becomes 0. Then here you will find that we replace S equals to lambda 2 here, this equals to 0, that means remaining term is of this S plus lambda 1 and S plus lambda 3. So, what we will get, we can write down as C2 minus lambda 2 plus lambda 1 here minus lambda 2 plus lambda 3, and from this you can easily get C2 equal to, C2 will get as A0 minus A1 lambda 2 plus A2 lambda 2 square divide by minus lambda 2 plus lambda 1 minus lambda 2 plus lambda 3. Sometimes if you take this equation as like this, B2 square B1S plus B naught, then in that A3 S cube plus A2 square plus A1S plus A naught, in that case this coefficient of this A0, A1, A2 will be replaced by B0, B1 and B2. So, now we have got C2. Similarly, we can also get the value of C3 and C1. How to get the value of C3? So, what is the best option here? Just like we have replaced S equals to lambda 2. So, what we can do here, we can replace S equals to lambda 3. So, if you replace S equals to lambda 3, there are two elements, there are three, first part, second part, third part, two part will be automatically 0, and we can directly get the values of C3. So, what we will do here, we replace S equals to minus lambda 3. So, if you replace S equals to lambda 3, so what we will get? We will get the equation of C3 as A0 minus lambda 3 into A1 plus A2 lambda 3 whole square divided by, so what will happen here? You got here lambda 2 plus lambda 1, lambda 2 plus lambda 3. So, here we will get minus lambda 3 plus lambda 1 minus lambda 3 plus lambda 2. So, we will get the value of C3. Now, to get the value of C1, so what is the option now? because here we have taken care of lambda 3 and this lambda 2, because we initially we replace s equals to lambda 2, s equals to lambda 3. So, now what we will do, we replace s equals to 0. So, if you replace s equals to 0 in these particular equations, so what we will get? We will get here a 0 c1 equals to lambda 2 lambda 3 plus c2 lambda 1 lambda 3 plus c3 lambda 1 into lambda 3 lambda 1 into lambda 2, that is a 0 equals to c1 lambda 2 lambda 3 c2 lambda 1 lambda 3 c3 lambda 1 lambda 2, and from this you can get the values of c1 equals to a 0 minus c2 lambda 1 into lambda 3 minus c3 lambda 1 into lambda 2 divided by lambda 2 into lambda 3. So, we have got the values of c1, c2 and c3, and as I told you earlier, normally we are taking a2, a1, a0 in the denominator and b2, b3, b3, b2, b1 in the numerator. So, I have done like this. If you change this, you can also get the similar type of replace. The condition thing is that instead of a2, a1, a0, we can get b2, b1 and b0. So, we have got c0, c1, c2 and c3. The main our purpose is to develop the state space model. Now, we see the output y of s equal to c1 plus s plus lambda 1 into u of s plus c2 s plus lambda 2 into u of s plus c3 s plus lambda 3 into u of s. Y of s equals to s plus lambda 1 into u of s, c2 s plus lambda 2 into u of s, and c3 equals to s plus lambda 3 into u of s. You can just see it, this equation. So, what we have done, this it has been multiplied by us. So, finally we got this. So, what we can do here, we can write this u of s plus lambda 1 as x1 of s, that is we can write c1 into x1 of s, that is this particular portion, plus c2 into x2 of s plus c3 into x3 of s, c1, c2, c3, x1, x2, x3 s. And what is x1 of s? So, x1 of s equal to u of s plus lambda 1. Now, what to do further? Because it is in s domain and we require in the time domain. So, here what we will do, we will apply inverse Laplace transform. So, when we apply inverse Laplace transform, what will happen? We will get s into x1s, that is equals to x1 dot, that is equals to minus lambda 1 into x1 plus u. Now, next we have got x1s. Similarly, we can go for the x2s. So, what is x2s? This x2s equals to u of s plus s plus lambda 2. So, how will you move? So, here we have got s into x2, that is x2 dot equals to minus lambda 2 into x2 plus u. Similarly, we can write x3s equals to u of s plus lambda 3. So, what will get? x3 dot equals to minus lambda 3 into x3 into u. So, we have got x1 dot, x2 dot and x3 dot. State space model is nothing but x dot equals to ax plus bu, that is your state space model is x dot equals to ax plus bu. So, how many states? There are 3 states. Therefore, we write this equation as x1 dot, x2 dot, x3 dot, that is, and now what is A matrix? A matrix is a system matrix and there is state x1, x2, x3 plus this is u. So, first state x1 dot equals to minus lambda 1 x1 plus u, but there are no terms of x2 and x3. Therefore, what we will do, we can write this is as minus lambda 1 0 0 x1 and is there term for u? Yes, there is a one term of u, that is 1 into u. So, we can write 1. Second x2 dot, what is x2 dot? x2 dot equals to, you just see here, minus lambda x2 plus u, but there are no terms for x1 and x3, terms for x1 and x3 are 0. So what will, how will you write? So x2 dot equals to 0 minus lambda to 0, and here there is also a term for u, that is 1. And now about the x3 dot. Now x3 dot equals to, what will write? 0 0 minus lambda 3. So lambda 1, lambda 2, lambda 3, because here also x3 dot, there are no terms for x1 and x2. Just see here, lambda 3 dot equals to lambda 3 x3 equal to u, and whereas this is a term for u. So this is a state space model, but again what we want, we require the model of our output. Output equals to yx, y equals to cx plus du, that is you want model y equals to cx plus du. C is the output matrix and D is the coupling matrix that we have seen last time. Now we have to write the equation for C. So how will you write down? You will find that you find y of s equals to c1 x1 of s, c2 x2 of s, c3 x3 of s, this is y of s. So here what we will do, we can also apply inverse Laplace to this equation. So what we will get, we can write y equals to c1 x1, c2 x2, c3 x3. We can write down in terms of y of t also, y of t, c1 x1 of t, c2 x2 of t, or c3 x3 of t also. Now we write the equation for y equals to c1, c2, c3, here x1, x1, x2, x3 plus, is there any term of d? No, you will find that there is no term of d is present. So we can write this as 0 into u. Therefore your final equation is y equals to cx plus du. So we got a matrix, a b matrix, this is a c matrix. And what are c1, c2, c3? c1, c2, c3 are called residues. They are called the residues. And again we will find that the most of the elements in this matrix A are 0. You will find that 0, 0, 0, 0. Therefore in introduction I have mentioned that number of terms, non-zero terms are very less, that is here lambda 1, lambda 2 and lambda 3, and remaining terms are 0. And again one thing is that in the output of u there are terms of only 1, 1, 1, and y is corresponding to c1, c2 and c3. So this type of modeling is called diagonal canonical form, diagonal canonical form, and this is a part 1. Why I am saying part 1? Because something is involved in this part 2. What is the problem here? The problem is that here we have taken the degree of denominator is greater than the degree of numerator. So that part we will see later on. But now here what is the thing, because we have developed the model, and now whatever model we develop, we need to do the simulation because we have to see the result. Therefore what we will do here, that is we have to develop the block diagram of a given state space model. So how to develop the block diagram? See, you see there are 3 states, x1 dot, x2 dot and x3 dot. So in this case there are 3 states, then how many integrators are there? There are requirement of the 3 integrators. So we will go for the first integrator. So we will draw, this is first integrator. So you see here I have shown one integrator. So what is the state? First state is x1, and how it come? It form x1 dot. See here this equation, x1 dot equals to minus lambda 1 x1, that means here we have to use minus lambda 1, this positive, plus u, that is u is there. So x1 dot equals to lambda 1 x1 plus u. Similarly we can do for the x2 dot and x3 dot. So how will you do it? So we write another integrator, we can draw another integrator. Now here is the block, here we can show minus lambda 2 u, here is x2, here x2 dot. Now similarly, there are another integrator required because we have x3 dot, so we can show another integrator. Here x3 dot, here is x3, here is u, here is minus lambda 3, and we have connected it. So x1 dot, x2 dot and x3 dot. So we have taken 3 integrator, integrator 1, integrator 2, integrator 3. So u is common, so we can connect it. So we can finally we can say this is u. So here we have drawn the block diagram of a system equations, that is x1 dot, x2 dot and x3 dot. But in the model we have output is y equals to cx plus du. So here we have to show the block diagram of the block diagram concerned with the output and the y, that is output is nothing but the y. So here we want to show output, so I have shown here one block, summing block, and now here y equals to c1 x1. So here x1 I can take c1 and here is coming is, so this is y. So y equals to c1 into x1. Similarly we want this is c2 x2, that be x2, this is c2. So y equals to c2 into x2, and lastly we have c3 into x3. So this is y c1 x1, c2 x2, c3 x3, and now other x1 dot equals to lambda 1 x1 into u, x2 dot equals to lambda 2 x2 into u, and x3 dot equals to lambda 3 into lambda t x3 into u. So here we will find that we have developed a block diagram of a diagonal canonical form. So all state equations, and this is state equations and this is a block diagram. And here one important thing is that here the degree of denominator is more than degree of numerator. And now here we have developed the block diagram. So here x1 dot, x2 dot, x3 dot, 3 integrator, integrator 1, integrator 2, integrator 3. Okay, then this is lambda 1, lambda 2, lambda 3, these are the eigenvalues. C1, C2, C3 are the output elements of the output matrix, and this is input u. Now these are some references, you can use these references. Normalize Oga Kushiho Uwata, IJ Nagarath. Thank you.